The next topic in module 4 is the radio wave propagation. So what is meant by radio wave propagation? It is the behavior of the radio waves as they travel from one point to another in the atmosphere, okay, or in the vacuum. So it can be mainly classified into three different types. Three types of propagation. The first one is called as your ground or surface wave propagation. Second one is called as your space or tropospheric wave propagation, and the third one is called as sky wave propagation. Okay, so what is meant by ground or surface wave propagation? These are the waves that is propagated in the Earth's surface. Okay, it is usually used in low frequency. Low frequency wave is being transmitted. For example, if this is your Earth's curvature, here there is a transmitting antenna, and if this is your receiving antenna, okay, receiving antenna, the wave will always follow the curvature of the Earth. Okay, so such waves are called, wave propagation is called as your ground or surface wave propagation that follows the curvature of the Earth. Example is your AM broadcast. Okay, so the second type is called as your space or tropospheric wave propagation. So space or tropospheric wave propagation is the type of propagation where you have your direct line of sight. Okay, line of sight propagation. That is, it directly reaches the receiving antenna. So if this is your transmitting antenna and if this is your receiving antenna, okay. So direct transmission, direct, it will be both the antennas if there is a line of sight between each other, then it is called as your space or tropospheric wave of propagation. That is, it directly reaches the receiving antenna. So it is around in the height of about 15 to 20 kilometer over the surface. Now there are mainly three components. Okay, so components of the space or tropospheric wave propagation is, your first component will be a direct line of sight waveform, just like the example what I have told you. The second one is called as your ground reflected wave. Suppose if the wave is coming from the transmitting antenna, it is transmitting the signal. Sometimes it reflects to the ground and then it reaches the receiver. Such type of reflected wave is called as your ground reflected wave. And there is in addition one more component which is used in satellite communication. Okay, so what is happening in your satellite communication is, if the transmitting antenna is sending the signal, it directly reaches the satellite. From the satellite, it reaches your receiver. Such type of wave propagation also comes under in this category, space or tropospheric wave propagation. Okay, the last one is called as your sky wave propagation. It is also known by another name, skip. Okay, so in this case of sky wave propagation, it is the, if this is your transmitting antenna and the receiving antenna, the signal will be propagated to the ionosphere layer. Okay, it goes to the ionosphere, reaches the ionosphere layer due to the reflection and refraction. So it will be reflected back to the receiving antenna. So this is called as your sky wave propagation. That is, from the transmitting antenna after reflection from the ionosphere, then it reaches the receiving antenna. Such waves are called as your sky wave propagation. So these are used for high frequency. Okay, even the space or tropospheric wave propagation is also used for high frequency. It depends on particular applications. Okay. So the next topic is called as your sampling theorem. So in short, the sampling theorem is a process by which you are going to convert a continuous time signal to a discrete time signal. Okay. So the example, let me give you an example. If I take this as your continuous time signal, okay. So if I take this as time, and if I take this as x of t, you are going to convert into a discrete time signal. So the time is now converted into discrete time signal at different instance of time. So you will be getting the signal like this. Okay, so this is how you will be getting the signal. Okay, so discrete time signal. Now, what is meant by sampling theorem? A continuous time signal can be completely represented in its samples and recovered back if the sampling frequency is twice of the highest frequency content of the signal. So sampling theorem states that this discretized signal can be reconstructed back only if the sampling frequency is greater than or equal to 2 times of Fm. So what is your Fs? Fs is nothing but your sampling frequency. Sampling frequency, and Fm is your maximum frequency of your modulating signal. Okay, so the condition for your sampling theorem is Fs should be greater than or equal to 2 times of Fm. Okay, so when you convert this into this signal into a spectrum in the frequency domain, you will be getting a band limited signal. Okay, it becomes x of f. So if I take this in frequency domain, it is called a spectrum. Okay, band limited signal between the bandwidth W2 minus W. So the sampled signal spectrum will be given like this. Okay, so this is your sampling signal spectrum. So this will be your band limited minus W. The center frequency will be sampled at Fs minus Fs, 2Fs, minus 2Fs, etc. Okay. So if Fs is greater than 2Fm, it is called as oversampling. Okay, if Fs is equal to 2Fm, this is called as Nyquist rate, and if Fs is less than 2Fm, it is called as undersampling. So if you want to reconstruct the original signal back in the receiver, then always it should follow the sampling theorem criteria, or the Nyquist rate Fs should be greater than or equal to 2 times of Fm, so that the signal can be reconstructed it correctly. Okay, so generally why do we go for this digitization is because the noise interference is in analog is more. The analog data cannot be digital transmitted. These are some of the important points why we go for your sampling. So the next topic what you are going to see is your digital modulation techniques. Okay, digital modulation techniques. So mainly your digital modulation techniques can be divided into 3 different types. First one is called as your amplitude shift keying. Second one is called as frequency shift keying. And the third one is called as your phase shift keying. So why it is called as shift keying technique is that on off. Okay, in this case of digital modulation, always your message signal is going to be digital. Either it will be on or either it will be off. Okay, so the message signal is digital in nature, digital, and your carrier signal is analog. Okay, so this is the specialty of your digital modulation technique. So if I take an example, so this amplitude shift keying, so it is called as ASK, FSK and PSK. Amplitude shift keying. So what is meant by amplitude shift keying? If the amplitude of the carrier wave is varied in accordance with that of your digital message signal, then it is called as amplitude shift keying. So amplitude of the carrier is varied. So in this case, amplitude of carrier is varied. So what is constant? Frequency and phase will remain as constant. Same definition as that of the analog. Okay, only difference is the message signal is digital in nature. So what is meant by frequency shift keying? The frequency of the carrier will be varying. Frequency of carrier will be varying. What will be constant? Amplitude and phase will be constant. Okay, what is meant by phase shift keying? The phase of the carrier will be varying. Frequency and amplitude will be constant. Okay, now let us see the waveforms. Okay, so in the case of amplitude shift keying, if I take your message signal as 1 0 1 1 0. Okay, so 1 0 1 1 0. So this is your message signal. If this is your message signal, now what is your carrier signal? You will be having a sinusoidal carrier signal. High frequency sinusoidal signal will be your C of t, right? So C of t. Now what will be your amplitude modulated signal, that is amplitude shift keying signal, ASK signal. So what will be your ASK? Whenever the message signal is positive, your signal will be present. Whenever it is 0, you will not get the signal. So it is also called by another name on off keying. So whenever your message signal is on, you will be getting your same carrier signal. Okay, whenever your message signal is off, it will be off. Okay, now again, whenever your message signal is on, you will be having the signal. Again it is 1, so you will be having the signal. So here it will be in the off condition. So this is on, this is off. So it is also called as on off keying technique. Okay, amplitude shift keying. So what is meant by frequency shift keying? The frequency shift keying is the frequency of the carrier wave is varied. Let me take the same example. Okay, 1 0 1 1 0 1 0 1 1 0. So same carrier signal you have. This will be your carrier signal. As before, your high frequency carrier signal C of t. Okay, now what will be your frequency shift keying? So when your message signal is positive, you will be having high frequency, and when your message signal is negative or 0, you will be having low frequency signal. So here you will be having high frequency because the message signal is positive. For 0, you will be having low frequency signal. So the frequency will be varying. Here it is both 1, so you will be having high frequency, whereas in this case it is 0. You will be having a low frequency signal. So what is happening in your phase shift keying? Let me take the same example. Okay, 0 1 1 0. So 1 0 1 1 0. So you have the same carrier wave. So the same carrier wave you have, high frequency carrier wave C of t. Now this is your FSK, right? Now what will be your PSK? PSK, whenever you have your message signal 1, okay, you will be getting the same carrier signal, and when there is a shift from 1 to 0 or 0 to 1, 0 to 1 or 1 to 0, there will be 180-degree phase shift. Okay, so for this example here you will be having the same signal, carrier signal. Now see here, there is a variation from 1 to 0. Now here you will be having a 180-degree phase shift. So here again there will be, okay. Now see here again you have 0 to 1. Now you will be having again 180-degree phase shift. This goes on. So you will be having M's and W's, it is also called as. So 180-degree phase shift, here also 180-degree phase shift. So these are the different types of digital modulation techniques used. Okay. So the next topic is your multiple access. So what is meant by multiple access? Multiple access is a process in which multiple mobile users can share the allotted spectrum in a most effective manner. For example, in your house, the Wi-Fi, right? Multiple users can share your internet through Wi-Fi. Okay. So this is a concept of your multiple access. There are 3 major types of multiple access. One is called as your FDMA, second one is called as TDMA, and the third one is called as your code division multiple access. FDMA stands for frequency division multiple access. TDMA, so this is frequency division multiple access. Similarly, TDMA stands for time division multiple access. CDMA stands for code division multiple access. So what is meant by multiple access? Different users. If this is one user with a mobile phone, similarly this is the second user with the mobile phone, okay, third user with the mobile phone, all can access the same Wi-Fi. Okay. So different users share the common internet. That is one of the examples. So what is meant by frequency division multiple access? The multiple users share the allotted spectrum in different frequencies. So if this is your frequency 1, F1, F2, okay. If this is your frequency and if I take this as time, so if this is your frequency F1 and if this is your frequency F2, the multiple users will be having allotted different frequencies and there will be a band between these two frequencies in order to avoid the interference. This is called as your guard band. Okay. So whereas in the case of TDMA, what will be the technology? In the case of TDMA, your multiple users will share the spectrum in different time slot. So if I take this as your frequency and time, now multiple users, different users will be given different time slot. Say for example T1, T2, T3, T4. So user 1 will be given T1, T2, T3. So each user will be given different time slots. Okay, that is called as TDMA. Whereas in the case of CDMA, multiple users will be given different codes. Okay, so it is also called by another name, spread spectrum multiple access, SSMA technology. So in the transmitter side and the receiver side, there will be a code which is called as your pseudo random code, to which your message signal will be added and then it will be given to the different users. So different users will be having different codes. That such technology is called as your CDMA technology. So the next topic is your FDD and TDD. So what is meant by FDD and TDD? FDD stands for frequency division duplex and TDD stands for time division duplex. Okay. So what is meant by duplex? Duplex is nothing but two-way communication, right? Two-way communication. Okay. So in the case of frequency division duplex, the two-way communication is possible at different frequencies. So two different frequencies are allotted. It is called as uplink frequency and downlink frequency. So what is called as your uplink frequency for transmission and downlink is for your reception. Okay. So two-way communication possible by means of two different frequencies at the same time. Okay, one can transmit and receive the message at the same time but with two different frequencies. That is called as frequency division duplex. So whereas in the case of time division duplex, the transmission and the reception, that is the two-way communication of is possible by means of same frequency, same carrier frequency but at different time. Okay, that is the difference between your frequency division duplex and time division duplex. So the next topic is your multipath and fading. Okay, so what is meant by multipath? Multipath, the name itself gives you the meaning. It takes different paths. Okay, the signal propagates due to the reflection. The rays can take several different paths. For example, the signals travel through the buildings, hills, mountains, etc. So due to reflection, it can take different paths from the transmitter to the receiver. This is called as multipath. So this multipath transmitted signal can be of constructive interference as well as destructive interference. The two signals which are taking the different paths, the receiver will receive the sum of the signals, right? If the sum of the signal is such that it is increasing or reinforcing the signal, then it is called as constructive interference. If it is if the sum is such that it is minimizing the signal level, then it is called as a destructive, cancelling the signal, then it is called as a destructive interference. So what is meant by fading? So the destructive interference which can make the received signal power drop to a very low level is called as your fading. So the next topic is your radio transmission and reception. Okay. So in the case of digital wireless communication, the radio transmission is mainly being done by four different types. Okay. One is your binary phase shift keying, quadrature phase shift keying, 16 QAM. QAM stands for quadrature amplitude modulation, and 64 QAM, that is 64 state quadrature amplitude modulation. So in the case of binary phase shift keying, you have 1 bits per symbol transmitted. Okay, either it will be 0 or 1 binary. QPSK in this case 2 bits per symbol. So you will be having a combination of 2 power 2 which is equal to 4 different states 0, 0, 1, 0, 0, 1 and 1, 1. Whereas in the case of 16 QAM you have 4 bits per symbol transmitted. So you will be having 2 power 4 which is equal to 16 different states. Okay. Similarly, in the case of 64 QAM, your transmission is 6 bits per symbol. So 2 power 6 which will be 64 different states. So if I can make a table, so BPSK, QPSK, 16 QAM and 64 QAM, bits per symbol, BPSK 1 bits per symbol, QPSK 2 bits per symbol, 16 QAM 4 bits per symbol and 64 QAM 6 bits per symbol. Whereas these are the different states. BPSK takes 2 states, that is either 0 or 1 with 0 and 180 degree phase shift. QPSK takes 4 different states. 16 QAM takes 16 different states and 64 QAM takes 64 different states. Okay. And the easy method is to convey the message using Constellation Diagram. So these are your Constellation Diagram which will signify the variation in your phase angle. See here. So here this is your Constellation Diagram for BPSK which consists of 2 different states. For QPSK it consists of your in phase and quadrature component with 4 different states. 16 QAM it has 16 different states. Okay. And for in the case of 64 QAM it has 64 different states. Okay, these points will give you the different states. So one of the example given in your text is your for signal transmission. See here you have the bits transmitted as transmitted information bit is given by 00101101. It is given to the modulator. So this is the example for QPSK. Okay, modulation. So it is given to the modulator. So what is happening in your QPSK? First the information bits has to be converted into symbols. How will it be converted to symbols? It will separate your odd components and even components. So if I separate this odd, even, odd, even, odd, even, odd, even. So your 0 will be your odd, right? 0, 1, 1, 0. So these are your odd components, and let me give by another color. So even component is 0, 0, 1, 1. Okay. So your odd components is 0, 1, 1, 0 and your even components is 0, 0, 1, 1. Okay. So these are your odd and the even components. 0, 1, 1, 0. Okay. So if I can then what is the next step? This will be grouped together and it will be multiplied by your in phase and quadrature component. So it will be, so this QPSK is quadrature. Quadrature means it consists of 4 different phases. So what are the 4 phases? They are 45 degree, 135 degree, 225 degree and 315 degree. Okay. So based on this 4 different phases, the data bits will be represented. Now what will be the combination? 0, 0, 1, 0, 1, 1 and 0, 1 will be your combination. 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 1 and 0, 1. This will be your transmitted bits which will be multiplied by your carrier signal sine and cos for the corresponding in phase and the quadrature component by your analog transmitter. So if I can draw the constellation diagram, so here we have seen your in phase and quadrature component which consists of 4 different states, right? So if this is 0 degree, 90 degree, what is this, 180 degree and 270 degree. So in the case of quadrature phase shift, how many different phases? You have 4 different phases. The phases are taken as 45 degree, 135 degree, 225 degree and 315 degree. So in the case of this example, what are the different states? You have 0, 0, 1, 0, 1, 1 and 0, 1. Okay. So these are the different states. This is your constellation diagram. So how can I give your waveform? So if I take the separation here of the symbols, this is for 0, 0, 1, 0, 1, 1, 0, 1. Okay. Let me do by an easy method. So here you can see that 0, 0 is giving a phase shift of 45 degrees. So normally when you take a sinusoidal waveform, it is this will be your 0 degree, 180 degree and 360 degree, right? So here it will be 90 degree, it will be 270 degree. Now what will be your 45 degree? 45 degree will be here 135 degree, 225 and 315 degree, right? So 45 degree the wave starts from here. So what will be your wave? Just start the replica with the carrier wave, because you have a carrier wave, sine and cos wave will be multiplied. The output will be the sum of the both your in phase and quadrature component. Okay, so this will be your 0 0 with 45 degree phase shift. Now what will be your next 1 0, which is having a 135 degree phase shift. So 135 degree the wave starts from here. Okay, so the wave will take this. Okay, so this will be your wave structure. Next is your 11 is having a phase shift of 225 degree. So here it is 135 degree. So 225 degree, so your wave is starting from the downward portion. So your 225 degree the wave starts from here. Okay, so this will be your 225 degree. And the last one is your 315 degree. So the 315 degree the wave starts from here. So it will be a W in shape. So this will be your 315 degree. So this will be your modulated QPSK signal, which will be your sum of both your in phase as well as quadrature component. Okay. So the next topic is the error management in digital wireless communication. There are two popular error management techniques. One is your forward error correction and the second one is called as your automatic repeat request. So what is meant by forward error correction means, it is a correction technique in which the information bits are transmitted along with some redundant bits. Redundant bits is also called as extra bits. Okay, extra bits. So it is called as a method of obtaining error control in data transmission, in which the transmitter sends redundant data and the receiver recognizes the data that contains no error. Okay, so it is just like guessing. The receiver will guess the message sent along with the redundant data. It will separate the redundant bits along with and recognizes the original data. So this is possible only if the number of errors is very small. So whereas in the case of automatic repeat request, it is a process in which the receiver detects the error and asks the transmitter to resend the message. So it is also known by the name as retransmission. Okay, so here the receiver detects the occurrence of an error and asks the sender to resend the message. So from the transmitter side, the data will be appended or will be added with some group of information, group of bits, that is called a cyclic redundancy check. Cyclic redundancy check. So in the receiver will check if the error has occurred. If the error has occurred, then it will ask the transmitter to resend the message once again. So this is the difference between your forward error correction and the automatic repeat request.